Hello everyone, thank you for attending. I choose the title HackDMI for the presentation. I hope you like it. The subtitle is Pwning HDMI for Fun and Profit. As you can see in the title, we have studied where HDMI can be used for attacks and where actual vulnerabilities exist. Before my talk, I'm going to introduce myself. My name is Changhyeon Moon, and I know my name is pretty hard to pronounce, so if you need to call my name, please call me just Moon. And I'm a mentee of BOB program, which is cybersecurity expert educating platform in South Korea. And in BOB, I'm a member of team Hacking. And my colleague Shingi is working as a researcher at a theory, and he's also mentor at BOB. And he's handsome. And it's such a great honor for me to be on the same slide as him. Yeah. Our team Hacking consists of 2 mentors and 1 PL, and 3 vulnerability track mentees and 2 consulting track mentees, and that's me. Actually, I was in Amsterdam last month. When I traveled to Europe, one of courses was Amsterdam. So because of it is hard to come to Europe from South Korea, I thought this was almost the last trip in my life, but yeah. So to see and enjoy everything, I went around really hard like this. Yeah. Actually, I had some hat here at the souvenir shop last month, but I'm here again. Thank you for Hipbit calling me a beautiful Amsterdam again. This is today's talk agenda. First, I will explain about the background of our project. What is HDMI and why we choose this project, some kind of that. And I will explain the HDMI protocols and explain the vulnerabilities we found with our fuzzer. And another fuzzer, actually that's my main part of our project. I will explain a little more specialized form of fuzzer. Okay, background. Literally, HDMI is interface for sending high definition video audio signal. This is just already what you know. But HDMI has several features. It can control connected devices and Ethernet communication without Ethernet cables and upstream audio data without audio cable. We took note of these features, and this is one of the reasons why we choose the project. And there are 5 types of HDMI, and type A with 19 pin is most common. And the pin map is as follows. I will explain more later. We checked those features and asked questions to people around us. Do you think you can hack into HDMI? And they said, what, is that possible? Or, well, I don't think so. Yeah. And we thought, what about the developers? Don't they think the same thing? And then we start the project. Prior to the project, we looked for previous studies, and there were already CVE, all of which were vulnerabilities of the kind of memory corruption that occurred in Linux kernel. Actually, we hope that there won't be any CVE because we wanted to be the first team to discover the vulnerability in HDMI. But there's already exists CVE, so we thought there were vulnerabilities in other devices, and I was sure we could find it. This is previous talk about HDMI. Hacking display made interesting at Black Hat Europe. What the HEC at 441 and high def fuzzing at DEFCON. Next, protocol detail. This is HDMI protocol overview. When we study protocols or make a fuzzer, we use the HDMI specs the most, and it is a great reference, actually. The video and audio data that we generally know is transmitted to a protocol called TMDS. There is a protocol called TDC to compromise the capabilities of the display. And the protocol for controlling the device is CC, Ethernet uses HCC, and audio upstream uses ARC. And these 2 protocols are collectively referred to as HEAC. Also use HPD as the line to verify that the HDMI is connected. And our project in our project, we choose that 3 protocol, CC, TDC, and HEAC. That is our attack vector, not TMDS. If you look at the HDMI port, it's made of 19 pins. Like that, this picture shows us looking at the port on the device, and the position of the pin on the cable is exactly opposite on the figure. Pin 1 to 12 are used for the TMDS protocol, 13 pin is used for the CC protocol, 14 pin is used for HEAC, 15 and 16 pin are used for TDC, and plus and minus uses pins 17 and 18. Lastly, 19 pin is used for hot plug detect. I've said a little bit about the CC before, but I'm sure didn't you get it right. So let me give you an example and once again explain the wall of CC. If various multimedia devices are connected by HDMI, as shown in the figure, the user can control all the devices with a remote control, which is HDMI CC. CC offers a variety of functions in the HDMI environment. The table below is from a multimedia company called Pulsate, which may have been updated a little more now. And you can see that each company uses a different name. The company wants to create a CC standard, but there seems to be no clear standard yet. So if you check the source code, there are many ways to implement CC. This has increased the likelihood of vulnerability of being present. Yeah. The CC protocol has a physical and logical address scheme. For devices that support CC, both physical and logical addresses are used, and for devices that do not support CC, only the physical address exists. The physical address is 4 digits long. The range is 0002 from 0002 FFFF and is not recognized if it is outside this range. Therefore, it has a 5 device type hierarchy. The format in which the address is assigned is easy to understand if you look at the image on the right. Logical address defines a device type. It exists only from 0 to 15, and each number refers to the type of device as shown in the right table. For example, TV is 0. Recording devices are 1, 2, or 9, depending on the device type. And logical address is allocated through the polling message. For example, if a recording device is connected, it sends the first address 1 to the broadcast. If the echo message comes in response, send the next address to broadcast, in this case 2. And if not, stop the procedure and retains that address. I hope you understand. The CC message frame, it has this structure. It consists of start bit, header block, and data block. And the first data block is for the block for opcode, and all other blocks are for operands. And the header block is used to specify the source and destination address of the CC message. And all blocks are composed of 10 bits, and maximum message size is 160 bits. That is a total of 10 blocks are available, including header block. Let me look at the block in more detail. The blocks are divided into information bits and control bits. And information bits are 8 bits and control bits are 2 bits. And information bits are dependent on context. It indicates source and destination address for header block, and opcode or operand for data block. And EOM in control bits stands for end of message, indicating that the message is the last message. And X stands for acknowledgement for a specific message. Next is DDC. In a DDC, the device is determined by 2 types. Reading EDID such as laptop or cell phone is called source device, and sending EDID data that such as TV or projector is called sync device. TDC is used to read sync's EDID to check the setting of the sync and its capabilities, and used in most display interfaces such as DVI as well as HDMI. TDC is transmitted by a serial communication called I2C. Let me explain in more detail the EDID that I mentioned. The EDID is metadata format for display devices to describe their capabilities to a video source such as set-top box. If you connect to HDMI and the screen does not appear, EDID is often a problem. This format is defined by a standard published by the PESA, and it is 120 bytes. As the various functions of the display increased, more information had to be transmitted. It's EDID why it was made. EEDID is an extension of the EDID used traditionally to illustrate more advanced features. More data can be transferred by adding to the default EDID 120 bytes. EEDID includes EDID and 120 bytes of extension data in a format called CEA 861D, and more extension can be added. EDID and CEA have the following structures. Because the data sent by the fuzzer is also this EDID data, we need to know a little bit about the data format. EDID 1.3 includes information such as horizontal size, vertical size, or color characteristics, etc. There's also extension flag, which means that the extension data follows the EDID structure. There's a careful thing when you mutate. You have to calculate the checksum of each EDID and include the zero padding for the CEA, because these values were often checked and dropped on the device. As I said before, TDC uses I2C. As you know, I2C is a serial computer bus invented in 1982 by Philips. It is widely used for attaching lower speed peripheral ICs to processors and microcontrollers in short distance intra-board communication. I2C uses only two bidirectional open collector lines, SDA and SCL, pulled up with resistors. Typical voltages used are 5 volt or 3.3 volt, although systems with other voltages are permitted. I2C basically communicates with the master-slave relationship, which is typically communicated by one master and a number of slaves. In a multimedia environment, multiple display devices may be attached to a single source device. So the source device becomes the I2C master, and the display device is in I2C slave. At TDC, handshakes exist for the source and sink to communicate. When HDMI is connected to a TV, 5 volt is entered into the TV from the source device. The sink has a separate EDID circuit, so even if the TV is turned off, the EDID is sent. When TV's input 5 volt, Haplo detect is low to high, and the source requests EDID, the TV receiving the request sends the EDID to the source. This is TDC. And this time, I'll explain about ARC. ARC is a protocol that extracts audio data from video audio data sent to TMDS and upstream audio data to the audio device. With ARC, audio can be transferred to other devices without the need for a complicated audio cable, and because it is connected by HDMI, audio devices can be controlled using CEC protocol. And if you have seen the word ARC on the back of your TV, you may already be benefiting from this protocol. Then how to use ARC? In order to use the ARC features, it is necessary to discover and control the capabilities of the devices in the respective paths using CEC. The figure below shows the initiation and termination process. Every messages are CEC message. And this is another case of ARC termination and initiation termination process. When using the audio return channel, the TV wants to find which audio formats are supported by the amplifier. It is also done through the CC by sending a request short audio discrete message. The process of obtaining the audio format is shown below, but it's not important. So far, we looked at a brief description of the CC, DDC, and ARC of the HDMI protocol. Now I will use them to make a further. Before that, I'm gonna drink some more. Oh, it's really thirsty. The materials needed to make the CC further are Pi serial, USB CC adapter, and HDMI cable. The Pi serial is a module for serial communication on Python. The USB-CC adapter is an adapter made by Pulsate that is designed to communicate CC to PC. The name USB-CC adapter is quite long to speak every time, so I will call this to P8. But other than this, there are other adapters, and some of them are not good for fuzzing because they only allow you to the commands already defined for users' convenience. So we choose this adapter to mutate as much data as possible. And you can also use libcc, not Pi serial, to use the adapter. libcc is a library developed by Pulsate that supports various hardware such as Raspberry Pi as well as USB-CC adapter itself. libcc is good for testing, but not for fuzzing. That's because libcc dropped the mutated data. And that is a P8 adapter, what I said before. But that's actually really tiny and cute. Yeah. P8 has its own message format, unlike sysframe. In the sys message, one block is expressed in 4-byte format. In the adapter, the first and last byte are fixed with FF and FE, indicating the beginning and end of the block. The second byte is the unique code digit of an adapter called message code, which is associated with control bits in CC frame. The third byte contains data bit to be entered into the information bits in the block of the CC frame. That is, if you want to transfer the 3 blocks of the CC frame, you have to send a message of 12 bytes. As a simple example, if you send a message to turn on the TV, you can see the following. Header blocks are expressed in this way, and data block is expressed in that way. 1.8 in header block is code that must be entered at the beginning of the message transmission in the adapter. And 0C in data block is the code that sets the EOM bits to 1. About 1 is source and 0 is destination logical address. And 4 in data block is OP code for turning on the TV. So if you configure the message and send it using the send message function, the TV will turn on. And we created a fuzzer for the 3 parts of the CC message frame. First, it is an OP code. 3.6 was excluded because it is an OP code to power off the device. The second is operand. We randomly selected a value from 00 to FF to transmit the operand for 14 blocks. The header block is fixed to the logical address of the target device. In the case of an OP code, to increase the probability of a crash, we use the list of OP codes that are likely to cause vulnerabilities. Finally, the message length. In the case of CC protocol, the maximum message size is fixed to 16 blocks, that is 160 bits. In addition, each block is recognized as a header block, an OP code, and operand in order. Therefore, data of various message size were transmitted, including messages that exceeded the maximum size. And we watch the device turn off turn off or reboot as a way to find a crash, or I check the internal system log or the log output to the bootloader. This photo shows fuzzing on smart TV. The adapter is connected to PC via USB and to a target device via HDMI. And to make sure that the fuzzer was running well and that the crash occurred, we used the UART port on the TV to check the log on the bootloader. Next is this fuzzer. Materials for making this fuzzer are Arduino Atmega and jumper cable and HDMI cable. Lastly, 4.7K resistors. As mentioned before, to transmit EDID, you need a device that supports I2C slave, which corresponds to the sync device. We used Arduino. About Raspberry Pi, there's a lot of talk about Raspberry Pi on the internet, but my conclusion is that only master mode is possible on Raspberry Pi. Why I used Arduino Atmega, not Uno, is because the EDID is 128 bytes or more, so using Uno is small in capacity, resulting in errors. For resistor, the typical resistor used for 5V voltage is selected and can be configured with the picture. 5V and SCL and SDA must be connected together by resistors. Each line is connected to each pin as shown on the slide. We stripped the wires and connected them directly to the HDMI pin, like this. However, we were angry because this was continually picked up. Fortunately, there was a hardware expert in our team, name is Greenie, so she renovated the HDMI cable. Yeah. First, the cut HDMI cable, find 5 lines connected to the pin, and solder the resistors and wires as if they were connected to the breadboard. That is the cable what we made. And I will show you the cable, but I didn't take away in my bag. Well, oh, there it is. Yep. This is the cable what we made. This side is HDMI port for connect fuzzing target, and this side is pins for connect Arduino. Yep. To fuzz through the HDMI cable, the process of connecting and disconnecting HDMI should be repeated. However, if you have to plug in and out the HDMI cable every time you send data, it's very, very inefficient and it will not be called a fuzzer. That is confirmed by the HPD signal. So we repeatedly send low and high to HPD pin, giving the same effect as connecting and disconnecting HDMI. To communicate the I2C in Arduino, you must use a library called Wire. You do not have to install it separately. You can use it if you already installed Arduino. By addressing the begin function, Arduino can be used in slave mode, and you can read and write with the read and write function. The onReceive function and the onRequest function are functions that register the function to be called when data is sent to Arduino and when requested by the master device. If you look at the wire.h and tw.h header file, the buffer length is 32. So if you send the EDID value of 128 bytes, the data we sent is dropped. Therefore, I modified the buffer length in the header file to 128 bytes as follows. Yep. And this slide is a flow of Arduino TDC fuzzer. When HPD is low to high, the source device requests an EDID from Arduino, and the requested Arduino calls up the onRequest callback function, which transmits the mutated EDID. The transmitted source device sends an ACK message to the Arduino, which outputs the data as the onReceive callback function is called. If the HPD is high to low and low to high again, the operation is repeated. The data that comes in an ASCII message is the number of bytes of data that the device has read. We created the data in the above three ways when mutating. First, each structure of EDID, and second, random among structures that are likely to cause vulnerabilities. Finally, a random value for all data. We use the bit flip, swap, and shift as mutation methods. And like CC further, we monitored the device being turned off or rebooted, and we determined whether it was crashed with a bootloader or a system log inside the device. And well, this is video of the DDS fuzzer. You will feel like you are fuzzing on graphics driver. The careful thing is you have already connected the 5V to the Arduino, and you supply electricity to the Arduino with USB or power adapter. Over voltage may cause problems with the Arduino or target device. In fact, when I'm running a fuzzer on my phone, I kept getting a message saying that detected an overcurrent on my phone while I was running without thinking about it. And my phone battery was working strangely for a while. Yeah, actually, it's actually horrible. About ARC, we thought vulnerability may exist in the area where the audio signal is returned via ARC. From what we found, ARC devices were using a lower version of the audio codec. Although they might have modified the lower version, it is likely that a vulnerability exists. So we fuzzing the codecs while we compile the source code in the device. This is the result of fuzzer shown above into the setup box. We found 3 vulnerabilities in VBox 3 global version. Unfortunately, we haven't found any exploitable vulnerability, but we think it makes sense in terms of showing that it is possible to attack using HDMI. Also, the last one was ignored because it had already physically contacted. I think this means that there are those who are interested in attacks via HDMI as well, and not strange study at all. First, the following is CC. In the main copy function, you can see a 1 byte stack overflow resulting in a memory leak. In closer look, the right function at the top of the slide is the CC message we sent. The header block and data blocks of the CC message are divided and stored, and we can see that the onTransact function in libHDMI CC contains the header and data blocks we sent. The readInt32 and readCstring functions are just that part. And if you look at the onEventUpdate function in libHDMI CC JNI, in main copy, which stores data blocks, the length of the message is incorrect and 1 byte overflow occurs. As a result, there's a possibility of system server crash or memory leak in print CC message buff function. And if you look at the TDC, you can see that the kernel panics and fails to reboot when I send the EDID. Also, we can see that the value is modified to 6.1 that I sent. It leads to denial of service. Yeah. And actually, this is my main part of the project. We made up about 2 fuzzers as well as other forms of fuzzers during the project, and I'll introduce them to you. As you saw in the previous slide's background, another fuzzer is Ubuntu fuzzer. The reason why we made this fuzzer was that, first of all, Arduino fuzzer didn't work properly in Ubuntu. The EDID within Ubuntu had to be updated to meet certain conditions, which had to be severely slowed down. So I thought, why don't you try to make a driver fuzzer? The thought of doing led to the making of a Ubuntu fuzzer. The environment is Ubuntu 16.4.5, and the built-in i915 and DRM driver is the target of fuzzing. The reason I choose i915 was just because my built-in graphics driver is i915 in my laptop. As a way to input the EDID, we tried to give it directly to the I2C device file, but it failed, and we had to find another way. That is hooking. In order to do that, I had to know how to get an EDID from Linux. After the source code auditing, we confirmed that the EDID was stored in the second parameter of the function, DRM to prove this EDID. After the function was completed, we used kproofs to hook the function. The kproofs are Linux's powerful debugging mechanism that dynamically hooks the kernel and allows for a variety of action through the callback function. This image is the code that becomes the basic skeleton of kproofs. In kp-adder, you can input the address of function to hook, as well as its symbol. Pre-handler is a method called before hooked instruction is executed, and post-handler is a method called after an instruction is executed. Also, you can control register value using regis. But the disadvantage of kproofs is that they can only be hooked and debugged when entering a function. So we used kretproof. Kretproof is a mechanism that has an extended function in kproofs. Unlike kproofs, data can be read and controlled by hooking at the end of function. With kretproof, you can control the return value immediately after the function ends, but I will control the buffer, which is the second parameter of the function, not the return value. KORSIMS is a table that manages all symbols in the kernel at ProKORSIMS. Check ProKORSIMS to see the list and address of the symbols currently accessible from Linux, and register them in the kretproof and hook them, like this. We choose the function that we identified before as a function to hook. The entry handler pre-saves the address of the buffer where the EDID will be stored as soon as it enters the function. Ret handler is a function called immediately after the function is terminated. It takes the address of the EDID buffer that was previously saved and mutates the data. But once you connect to HDMI, you can only perform once, so we have to call the hooked function repeatedly. However, the HDMI cable cannot be repeatedly plugged in and out, so we had to find another way. Previously, I was told that I would give HPD to effect of putting it away from Arduino fuzzer. So I used HPD in Arduino, but it did not working. I don't know why. So if I repeatedly 5-volt plug pins in and out of the Arduino, the function was triggered, but it was complicated and cost me to do this automatically. So first I checked the core stack. There are various tools such as SystemTap to trace the core stack, but I used ftrace. Ftrace is an internal tracer designed to help out developers and designers of systems to find what is going on inside the kernel. The files for using ftrace are in the syskernel debug tracing path. There are several types of tracers. Their types are defined in available trace file, and the traceable functions exist in the available functions file. Trace results are stored in name is trace file in the same path. If you use a program called tracecmd, you can use ftrace a little more conveniently, but I only used tracecmd as an assistant because using the echo command is more intuitive for me. For ftrace, the option is set by inserting a value into the file with the echo command as shown in the picture. If you set it to the first line in the figure, it traces when the DRM to prove DDC EDID function is called. If you give funcstack trace as an option, the ftrace outputs the core stack when the function is called. Then put 1 into tracing on file and starts trace from them. After connecting the HDMI cable once and end the tracing and check the trace file, you can see the call stack like the picture. Here I check the first function that called the hooked function, DRM mode get connector. Actually, the first time I run a xrender command, we triggered the function that was hooked up and used it to fuzzing, but there was too much noise in xrender. So I looked again at the Linux source code and found a way to do function triggers in some other way. If you look at the call stack, the function is called from the IOSTL. We did source code auditing to check the IOSTL code needed to make the IOSTL call, and confirm the corresponding IOSTL code, DRM IOSTL mode get connector, as shown in the figure. And I found a library called libdrm while I was trying to find a way to call using this IOSTL code. And I tried to install it, but failed. So many failed, yeah. Because the conditions for compile were tricky, and something was wrong and could not be installed. So I started with this code. I found the necessary code, scrapped it up, then combined it into a program that calls the DRM mode get connector. Yeah. The resulting fuzzer is operated in this form as a whole. Connect the HDMI cable to the sync device and Ubuntu, run the function call program created using the libdrm, and mutating by hooking krepproof. The seed for fuzzing is the EDID value of the sync device, so I cannot mutate it on using multiple seeds, but I think it's okay because EDID is not that big. And actually, I know this is weird, but the performance was better than the Arduino fuzzer. And I made this fuzzer, but unfortunately, there was no such result yet. But in this way, you can make a fuzzer that targets other graphics driver in Linux. So try it. And what about Windows? I also analyzed it on Windows to make a fuzzer like Ubuntu. The target was an Intel graphics driver called IGDKMD64, and I debugged the kernel using WinDBG. We identified the function, the location of getting the EDID with repeated reversing. Actually, BA command is really useful to analyze. But unfortunately, I couldn't find the kernel debugging mechanism such as the kproofs and the ftrace on Linux, so I couldn't make a fuzzer. Yeah. So if you know the method, please let me know after the session, please. I want to make a Windows fuzzer. And we put together a way to make a fuzzer and published it in ebook. Title is Fuzzer Development Guide for HDMI Security Analysis. Price is €3. And I'm sorry, but there's only Korean version. I will try to make an English version maybe later, maybe. It's maybe, yeah. Lastly, I would like to introduce our future work. HEC has not yet had a lot of appliance in it, so we could not analyze it during this project, but HDMI forum will surely come out with HEC-enabled devices because multimedia devices companies gather together to make specifications. So we will analyze the vulnerability to it, and we will also analyze the eARC protocol added in HDMI 2.1 and upgrade our fuzzer. Actually, at the end of our project, finding vulnerabilities in HDMI should really be a good target. If there is a vulnerability, it does not take a long time because a small amount of fuzzer will cause a crash. Therefore, we will find vulnerabilities by running fuzzers on various other devices. And finally, we will keep the world safe from HDMI attacks. And I will continue to study on the unexpected attacks attack vector like HDMI or audio jack or USB, etc., some kind of that. Yeah. And it's too early end, but that is the end of my presentation. As for the question, I can't answer the real-time question right now because I'm not good at English. So if you need any question, the best way is contact me to my email. This is my email. But if you wanna ask me right now, after session, I will somewhere in this conference. So come to me and I will answer you using my translator. Maybe like this. Oh my God, my internet is disconnected. Well, actually, yeah. Actually, there show us hello world. I wanted to show hello world to translate my translator, but sorry, yeah. Oh yeah, that is, yeah. Thank you.